Okay, let's practice some more on determining rate laws of reaction, including units on rate constants, the initial rates to determine the order of reaction, and rate constant overall units, the overall rate law, putting it all together. So first order reactions. If a reaction is first order, suppose reactant A goes to products. The rate for this would be rate equals K times concentration of A. Because again, first order means that I have a little implied 1 up here. We just don't write the 1. If it is first order, the rate is proportional to the concentration of A. If I double the concentration of A, the rate doubles. If I triple the concentration of A, the rate triples. If I quadruple the concentration of A, the rate triples. So if the rate was equal to 2, if I change this to concentration, if I multiply this by 2 and it's 4, it's now 4. If I multiply this by 6, it's now 6. I know that's simplified math, but that's basic, and it won't be that simple. That's basically what it means. If I double it, the rate doubles. If I triple the concentration, the rate triples. If I quadruple the concentration, the rate quadruples. Or if I triple, quadruple, quadruple. Second order, suppose A goes to products, the rate is written as rate equals K times concentration of A squared. Here, the rate is proportional to the square of A, meaning if I double A, the rate is going to quadruple. If I triple A, the rate is times 9, because 2 squared is 4, 3 squared is 9, quadruple, 4 squared is 16. So if you see that you've doubled the rate, if you've seen that you've doubled the concentration of a species and the rate is now 4 times faster, that means it is second order. If you see that you have doubled the rate and the rate is only twice as fast, it is first order. If it's zero order, suppose A goes to products, the rate here is just equal to K, your proportionality constant. Because again, rate of K times concentration of A to 0, this entire term goes to 1, giving me rate is equal to K. Basically what it means is the rate is completely independent on the concentration of A. The rate stays constant, it has no dependence on that concentration of reactant A. If I double the concentration, the rate remains unchanged. If I triple the concentration, the rate remains unchanged. If I quadruple the concentration, the rate remains unchanged. It has no effect at all on the reaction if it's doubled, tripled, quadrupled, etc. The rate will remain constant because it's only dependent upon your proportionality constant or your rate constant. So, units of the rate constant, I need you guys to remember rate is always molar per second. If this is first order, A has a concentration of molarity. I need this to equal molar per second, so K will have units of 1 over second. You could say 1 over second, or you can say seconds to the minus 1. If the reaction is second order, again, rate must have molar per second. This is now m squared, so this will be 1 over molar seconds, because that will cancel out one of these and give me molar per second overall. So K is equal to 1 over molar seconds, or you can say molar to the minus 1, seconds to the minus 1. You may even see this written as liters per mole second because it means the same thing. If it is third order, again, rate must be molar per second. This is molar cubed. To get this to work out, this must be 1 over molar squared seconds. You can also write this as molar to the minus 2, seconds to the minus 1, etc. Whatever you need to do, I don't care, but K will have whatever units it needs in order for the rate to have units of molar per second. So let's work an example. The initial rate of a reaction A plus B going to C was measured for several different starting concentrations of A and B. The results were as follows in the table above. I want you to calculate the rate law, the magnitude of the rate constant, and the rate of reaction when the concentration of A is 0.050 molar and the concentration of B is 0.1 molar. So you can do this two different ways. You can do this mathematically or by inspection. I'm going to figure out this rate law by inspection. First, what's the general rule or general rate law? Rate is equal to K times concentration of A raised to some power times concentration of B raised to some power. I look at the experiment itself and I see from run 1 to run 2, the concentration of A stayed the same, but the concentration of B was doubled. So this was times 2. I then look at the rate and see this was unchanged. This was constant. I doubled the concentration of B, but nothing happened to the overall reaction. What that means is that the reaction is 0 with order with respect to B. For reaction 1 to 2, concentration of B was doubled, rate was no change. Then I look and I see from reactants 1 to 3, I want to be able to compare the same thing. So if I can do 1 to 3, it makes it easier. If I look at reactants 1 to 3, the concentration of A was doubled. The concentration of, or the rate though, was actually 4 times faster. I doubled concentration, my rate quadrupled. That is second order with respect to A. Between reactions 1 and 3, the concentration of A was doubled, the rate was quadrupled. So then X is equal to 2. That's what I mean by the by inspection method. I'm inspecting the changes in rates to determine the new rate law. So the rate law, rate is equal to K times the concentration of A squared. We don't even put B in here because it's 0 order with respect to B. B had no change on the rate of this reaction. The magnitude of the rate constant. The magnitude means the value. I'm now going to pick any one of my runs, 1, 2, or 3. I usually just go for 1 because it's the easiest. It will be constant throughout, though. I'm going to plug in all my values into my rate law to solve for K. So I've got 4.0 times 10 to the minus 5 is equal to the rate constant K times the concentration of A, quantity squared. Solve for K. 4.0 times 10 to the minus 5th over 0.100 quantity squared gives me a value of 4.0 times 10 to the minus 3rd, and this is molar to the minus 1, second to the minus 1. Why do I know my units? Because I know rate is equal to the concentration of A, quantity squared. Rate needs molar per second. The K belongs in here. Molarity A squared is molarity squared. So to get to units of molar per second, I must have this 1 over molar seconds, or molar to the minus 1, seconds to the minus 1. So the magnitude of my rate constant, 4.0 times 10 to the minus 3rd molar per second, or 1 over molar seconds. Molar to the minus 1, second to the minus 1. The rate of reaction when the concentration of A is equal to 0.05 molar and B is equal to 0.1 molar. Now I plug everything in. I know my rate is equal to 4.0 times 10 to the minus 3rd molar to the minus 1, seconds to the minus 1, times the concentration of A, 0.050, quantity squared, and the concentration of B makes no effect on this reaction, so I leave it out. The rate is equal to 1.0 times 10 to the minus 5 molar per second when the concentration of A is 0.050 molar and B is 0.100 molar. That was just finding to show extra work. Sorry, I forgot that I left space for that one. Okay, let's do another example. Consider the reaction A plus B going to products. The initial rate of this reaction was measured for several different initial concentrations of A and B to determine the rate law. When I say determine the rate law, even though I don't specify it, I mean the overall rate law and the K value. I want everything. But when I look at these values, I see 1 to 2, my concentration of A is times, like, not doubled, it's like times 1.5. And from 1 to 3, my concentration of B is really funky too. This is not easy to do by inspection. I need to do this by math. So we can do inspection when they're easy, doubled, tripled, etc. But here, where they're not easy like that, I've got to do it by math. I know my general rate law is equal to K times the concentration of A raised to some value times the concentration of B raised to some value. And I want to determine what this is. But again, when I go from 1 to 2, my concentration of A is times 1.5. My rate, I can't tell. So I'm going to solve this with math. The way you do this is you compare the two different rate laws. So I'm going to compare for A, I'm going to compare 1 and 2 because that's where it's been been changed. And then for B, I'm going to compare 1 and 3. I'm going to take the bigger numbers divided by the smaller numbers. So in number 2, the concentration of A is bigger and the rate is bigger. I'm going to say the rate law of number 2 divided by the rate law of number 1. The rate is equal to K times concentration of A to the X times B to the Y. This is for rate 2. And I'm going to divide this by rate from reaction 1 times concentration of K, A in 1, B raised to the Y in reaction 1. I'm then going to plug in my values. Rate 2, the initial rate of the second reaction, is 0.027. The initial rate of the first reaction is 0.012. My K value, I don't know what it is, but I do know it's constant, so they cancel each other out. My concentration of B, you can go ahead and plug it in here, but you don't need to. It stays constant between both reactions, and Y as well will stay constant. This simplifies this reaction for me, so now I only have to say 0.15 raised to the power of X divided by 0.10 raised to the power of X. So I've got 0.027 divided by 0.012, and remember 0.15 divided by 0.10. This whole thing is raised to the power of X. We can simplify that by log rules. Do the math. This gives me 2.25 equals 1.5 raised to the X. If you can solve it from here, great. I'm not great at that. I'm going to take the log of both sides. The log of 2.25 is equal to X times the log of 1.5. Solve for X. And X is equal to the log 2.25 divided by the log of 1.5. That gives me a value of 2. That tells me that when I'm looking at my rate law, I have just solved this value of X. I've determined that this value is equal to 2. I'm going to follow the same process for B. And I did leave extra, or I did not leave extra paper down here, so I do need to erase this to do it. But I'm going to follow the exact same process for B. Please pause the video if you need to write this stuff down, though. So when I initially go to B, my first inclination is always to compare reactions 1 to whatever else. But I can't really compare 1 to 3 because the concentration of A is changing between 1 and 3. What you need to find is the two reactions where the other reactant remains constant and you're only changing one of them. So what I really need to do is I see that it stays constant between 2 and 3 for concentration A, but it changes for B. So I really need to compare the reaction rates between 2 and 3 so that A is staying constant, so I can ignore it when I do the math, and that B is changing. If you don't do that, you have to keep A in the fractions in the math that you're doing. What do I mean by that? I'm going to take number 2 divided by number 3, because number 2 is a little bit bigger, my rate of 2 is equal to K times concentration of A, we now know that's squared, times concentration of B raised to the Y. This is going to be divided by rate of 3. Here, A and 2 and A and 3 are the same, which means I can cross them out. I can ignore them. If I went and did reactions 1 to 3, I would not be able to ignore A. Does that mean you can use it? Yeah, of course it does. I just like simplifying my math to use as few numbers as possible. So I'm going to use the ones where only one species is changing concentration. Plug in what we know. We've got 0.027 divided by 0.019 equal to the concentration of B, 0.60 raised to the Y over 0.42 raised to the Y, which is of course the same as 0.60 divided by 0.42 quantity raised to the Y. When you do this math, 0.027 divided by 0.019 gives you 1.42, and 0.60 divided by 0.42 gives you 1.43 raised to the Y. Now you can go ahead and take the logs of both sides and you'll get to the same point, or you can recognize these numbers the same, Y equals 1. I don't care which way you do it, but that's what I mean by that. The overall rate here, the overall rate law, is equal to K times concentration of A squared times concentration of B. Now, how would I find the value of K if I wanted it? I would plug my values in from the reaction itself to find the value of K. So the rate equals K times concentration of A squared times concentration of B. In run 1, we have a rate of 0.012. This is equal to K, and this is molar per second, times 0.10 quantity squared times 0.60. And I don't actually have this calculated out yet, so 1 second. I get a K value of 200. There should be 2 sig figs there, so 2.0 times 10 to the second. And I still need units. Rate is equal to 2.0 times 10 to the second. What are my units here? This is molar squared, this is molar. So this must be 1 over molar squared seconds to be able to cancel everything out and get to molar seconds on the rate side. And there's my answer. Let's do a few more examples like this. First, I do want you to be careful here. I want you to remember to not confuse rate constant with reaction rate and rate law. Those can get kind of confusing for students, and I understand that their terms are very similar. The rate law has the form rate equals K times concentration of A raised to some power times concentration of B raised to a power times concentration of C raised to power. MNP, XYZ, I don't care what letters you use. I just use different letters to make it very apparent that they are not the same as the coefficients on the reaction. The rate law must be experimentally determined. We can predict them, but the truth always comes from experimentation. The rate constant is K, and it's a lowercase k. Very distinctly a lowercase k, because we're going to use capital K throughout all of equilibrium, so please use a lowercase k. K varies with temperature, therefore the temperature should be specified. A reaction with a larger K value is faster than one with a smaller K, and K is independent of the reaction concentration. The reaction rate is your rate. The rate of the disappearance of your reactant, the rate of the appearance of your product. Rate is always in units of molar per second. Please remember that you cannot determine the rate law just by looking at a balanced chemical equation. The rate law for a given reaction must be determined experimentally. We can predict things, but experiment always trumps prediction. For example, for this reaction, CHCl3 plus Cl2 give me CCl4 and HCl. So chloroform reacts with chlorine to give you carbon tetrachloride. I apologize. I'm trying to get these videos done for you guys. My brain is tired. Plus hydrochloric or HCl gas. HCl gas, which actually bubbled through water to form hydrochloric acid. But you could predict a rate law for this, but the experimentally determined rate law is actually the rate is equal to your proportionality constant K, or your rate constant K, times the concentration of chloroform raised to the first power times the concentration of chlorine to the 1/2. So you can have fractions here. I would not be able to predict this value. I would not predict this without experimentation. But experimentation is where we get the true answers. So let's work a couple more examples here. This is the result from 4 experiments to study this reaction. I want you to tell me the overall rate law for this reaction. Remember rate law? Rate is equal to your rate constant times, looking at all your reactants, BrO3 minus raised to some power x, Br minus raised to some power y, and H plus raised to some power z. You can do this mathematically, or you can do it by inspection. I prefer by inspection when I can. So I'm going to look first at experiment 1. I see everything is 0.1 molar. Cool. I look at experiment 2, and I see that my concentration of BrO3 minus has been doubled. The concentration of the other species has remained the same. So from experiment 1 to 2, the concentration of BrO3 minus has doubled. I look at the rate. The rate has also doubled. That means this is first order with respect to BrO3 minus. I look at the second one. I see from the in the third reaction, the concentration of BrO3 minus is doubled, and the concentration of Br minus is doubled, but the concentration of H plus remains at 0.1. So for this reaction, I'm going to compare reactants 2 and 3 because the concentration of BrO3 minus is not changing from 2 to 3. Neither is the concentration of H plus, but the concentration of Br minus is. So from 1 to 3, sorry, that should say 2. From 2 to 3, the concentration of Br minus has been doubled. The rate, 1.6 times 10 to the -3rd to 3.2 times 10 to the -3rd, is also doubled, which means this is first order with respect to Br minus as well. So now I have determined the values of x and y to both be 1. I'm going to show you guys how to do this mathematically in just a minute, but I like doing it by inspection when I can. So then let's look at the last one. The concentration of H plus has been doubled. I can either use reaction 1 to 4. Let's see. Yeah, reaction 1 to 4 is the only reaction I can use. The only one where everything else stayed constant except the concentration of H plus. So from reaction 1 to 4, the concentration of H plus has been doubled. The rate is actually 4 times faster. 3.2 times 10 to the -3rd is 4 times faster than 8 times 10 to the -4. So I doubled concentration, but my rate quadrupled, which means this is second order. Which means this value of z is 2. The way we actually write that, we don't write those ones. We would write the rate is equal to K times BrO3 minus times Br minus times H plus squared. What is those units on K though? Well, if I've got molar here, molar squared here, and I need molar per second, my K value must always have seconds in the bottom, but I can only have 1 molar coming out, and I've got 4 in here. So it must be 1 over molar cubed seconds. Let's go ahead and do this with math as well, so I can show you the math of it. I'm going to do that on the next page, though, so screenshot or something this picture because I don't have it on the next page. So to do this by math, we would do the same thing we just did. We're going to compare them instead of by inspection, by math. I saw that from reaction 1 to 2, my concentration of BrO3 minus was doubled. It went from 0.1 molar to 0.2 molar, but the concentrations of all the other species remain the same. At 0.1 molar, I had an initial rate of 8.0 times 10 to the minus 4, and once doubled, I had a concentration of 1.6 times 10 to the minus 3. So I'm going to say rate of 2 divided by rate of 1, K times BrO3 minus raised to the X times Br minus raised to Y times H plus raised to Z over K times BrO3 minus raised to X. Again, this is for reaction 2. This is for reaction 1. I know that the concentration of Br minus stayed constant, H plus stayed constant, and my proportional or my rate constant stays constant. So I can simplify this down and say, okay, 1.6 times 10 to the minus third divided by 8.0 times 10 to the minus 4. These are both molar per second, but the units cancel out, is equal to the concentration of BrO3 minus for reaction 2, 0.020, divided by the concentration from reaction 1, 0.010, raised to the power of X. When I do this math, I find this to be 2, this to be 2, this to be X. If I take the log of both sides, X is equal to the log of 2 divided by the log of 2. X equals 1. You can follow that process for the others as well, solving them the exact same way. I don't particularly like that method if I don't have to do it. If I can do it by inspection, I will do it by inspection. If I can't, I will do it by math. But you can always solve all of these by math. You will get to the right point. For my class, I don't care if you do it by inspection or math. You have to recognize when you must use math, but you're welcome to do it by inspection. So, initial rates for this reaction, NH4 plus NO2 minus, giving me N2 plus 2H2O. When I look at NH4 plus, I see that it stayed constant between reactions 1 and 2, but 2 and 3 has changed. And then I look at the initial concentration of NO2 minus, and I see that it has changed between reactions 1 and 2, but stayed constant from 2 to 3. I know that the rate law is equal to K times concentration of NH4 plus raised to some value X times concentration of NO2 minus raised to some value Y. And I'm trying to find out what those values are. So I want to find the reaction where the concentration of one species has changed but not the other. Between reactions 2 and 3, the concentration of NO2 has remained constant, but the concentration of NH4 has doubled. The concentration has doubled, and I look then at the rates, and I see 5.4 times 10 to the minus 7 and 2.7 times 10 to the minus 7. The concentration has doubled. The rate has doubled. Therefore, it is order of with respect to 1 for NH4 plus. Between reactions 1 and 2, the concentration of NO2 has doubled. The concentration and the rate of reaction has also doubled. Therefore, the value of Y is also 1. And if I wanted to find my units here, molar per second, molar, because they're each 1 over molar seconds. So the rate here is equal to K with units molar to the minus 1 second to the minus 1 times the concentration of NH4 plus times NO2 minus. Again, you're welcome to do it by math. It's just, for me, faster to do it without the math. And that's the end of that module.